Hi folks, welcome back to Physics with Captain Rod. I'm making this video to help you out with numbers 20 and 21 here in your Gauss's law homework. So let's see, a plane L by L hinged and can rotate about the y-axis. Find expression for the electric flux through the plane for each condition below. So I gotta scroll down to see the conditions. Now, right off the bat, all right, so the area, right, can be calculated. So this area in the plane here can easily be calculated, right? That's just a square. So our area, right, is equal to L squared. Okay, conditions below. Find the electric field. Oh, I'm sorry. An electric field magnitude E sub O is in the x direction and the angle theta for alpha is 30 degrees. So you have to imagine an electric field. I'll go ahead and draw an electric field vector this way. Now, these are kind of three-dimensional problems. I'm going to try to help you out with another picture. If we were looking from a top view, I'll draw this maybe right over here. All right, here's what we would see. The x-axis, we would see the z-axis down, and the y-axis would be pointing us right in the eye, basically, all right? We would see this length right here would look like this in the picture, and the angle alpha is that angle right there. Let's see, 30 degrees equals alpha. That's what we would see. Now, the electric field vector in this picture points, doesn't matter where I draw it, I'll go ahead and draw one right here. Points like this. Now, when you calculate flux, right, that's equal to EA cosine theta. And again, remember, the theta is between the electric field vector and the normal. So here's our electric field vector. The normal is this way in our picture. Now remember, the normal means perpendicular to the area. Now, just because you see an angle in a problem, that doesn't mean it's the one you need. All right, you need this angle right there for the flux calculation, and that's not the 30 degrees. And I'll let you folks think about this. All right, look at this triangle right here, this green triangle. This is a 30-degree angle. Then ask yourself, okay, what is this angle? And that will tell you what this one is. So that should be enough to get part A done. Right? So make sure you get the right angle. Part B, there's an electric field and the angle is 0. Draw a similar picture and just set that angle to 0. That'll get that done for you. See? Okay, electric field is in the plus J direction. All right, so now draw a similar picture, except the electric field is in the plus J. So the electric field is this way for that very last problem. So what would be a good, let me think about how to answer that. Yeah, again, do a top view of that. And the normal is in the same direction. Then ask yourself, what is the angle between the normal and the electric field? And I'll help you out a little further. Remember this original picture? This is like looking right down at the y-axis. So the electric field is actually coming at us. We might do something like this. Circle dot is a good way to express a vector coming at you. So that should get you through that last part, hopefully. Okay, 21, let's see. Consider the geometry sitting in a uniform electric field. Find the flux through each of the 5 surfaces. So electric flux, again, remember, is EA cosine theta. And again, remember the theta is always between the electric field vector and the normal. So in this problem, our electric field vector is pointing this way, right? Because it says minus I direction. So let's talk about this back face, this one right here. Ask yourself which way the normal is. Now, this is a 3-dimensional geometry. Remember that normals always make a right angle to the surface, and outward normal is considered positive. Right? So draw a normal vector somewhere on the surface, then ask yourself, what is the angle between that normal and this electric field vector? Let's talk about these side surfaces. I'll call them like 2 and 3. So I'm talking about this stuff right here, okay? Draw a normal on this surface. And then ask yourself, what is the angle between the electric field and the normal? And that should give you, that should tell you what the flux is through that surface and the back surface. You're going to get the same answer. Then do the bottom surface, this stuff right here. Again, draw the normal to that surface with outward positive. And then ask yourself, what is the angle between that normal and the electric field vector? And then therefore, what is the cosine of that angle? That will help you out. Now here, okay, this one is a little bit, I guess, trickier. Start by drawing the normal. But this geometry right here, we don't know this. There's not enough information in this picture to get that because we don't know this distance nor this length. But think about what Gauss's law has to say about the total flux through that closed surface, like the entire thing. Keeping in mind there is no charge inside that surface. So that should allow you to calculate the total flux the flux through every surface. I hope that this helps. Have a great day.